All right, so we are going to go over chapter 10.1, which looks at temperature and heat. So, a little bit different this particular chapter will be than some of the other chapters. We're still looking at energy transformation, but not in the form of what we've usually been doing as far as force or something like that. We're looking at how heat energy gets transferred and how temperature changes due to that heat capacity, changes in phase, like going from a solid to a liquid or a liquid to a gas, that kind of thing. So, a lot of the second law of thermodynamics is what we're going to be looking at. So, some things that will be familiar from chemistry because there's a lot of chemistry in this particular section. Um, so some things to remember. Experiments show that particles in a hot object move faster than those in a cold object. And I think we did a little PhET simulation earlier in the year looking at that, how if you heat something up, those particles are moving faster. They have greater kinetic energy. Okay. This observation leads to the physical definition of temperature. And temperature is, and you need to know this definition, proportional to the average kinetic energy of the particles in the substance. It is not the kinetic energy of all of the particles because not all the particles are going the same, have the same kinetic energy, but it is proportional to the average kinetic energy. Okay. Kinetic energy of an individual particle in a substance changes with time. So it's just the average that is related to the temperature. Okay. So only the average value of its kinetic energy is related to temperature. Okay. So let's move this up here. Come on, go up there. All right. So the total amount of energy in a substance is, or the sum of all its kinetic energy and potential energy, is called thermal energy. So again, that's another definition that you need to make sure you put in your notes. So the total amount of energy in a substance, that means all of its kinetic and potential energy, that is what we call its thermal energy. An object's thermal energy is the random motion of its particles. That's its kinetic energy. And the separation orientation of its particles relative to each other. That's its potential energy. So they have the potential to collide, the potential to collide and maybe form a new compound or form a molecule. So those would be considered potential energy. Um, Kinetic energy, of course, would just be the motion of the particles. Adding thermal energy to a system is known as heating. So when we heat something up, what we're doing is we are adding thermal energy. When we remove thermal energy, that's cooling. Okay, so these are things you kind of know already, but you need to get the correct scientific terms. And um, knowing that definition of thermal energy as opposed to just the temperature of something. Come on. There we go. So in your book looks at this thing called a U-tube, and it's just like it sounds. It's a tube in the shape of a U, like that. Um, and normally, if the water level on both sides is equal, and they said this is in your book. So the height of the water on the two sides of the U-tube is like temperature. The total amount of water is like the thermal energy. The U-tube is in equilibrium when the height of the water is the same on both sides. Okay, so get that picture in your mind. I have drawn up here. So if we have a U-tube and we have water at the same height on both sides, we say that that is in equilibrium. Okay, all right. I'm going to actually try to leave that up there. Yeah. So here's our example. So the system in equilibrium is when the water levels are on both sides. The height of the water is going to represent, and as said, this is just an analogy, it's not literal. The height of the water is going to represent our temperature, which remember is the average kinetic energy. The amount of water is our thermal energy, which is the sum of our kinetic energy and our potential energy. And so when they're the same on both sides, then our system is in equilibrium. Even though there's more water on the left side over here than on the right side, we still say it's in equilibrium because they're at the same height. So as the figure indicates below, when the water level is greater on one side of the tube, water flows to the other side of the tube, even if that side has more water. So if we look over here now at this particular figure, you can see that we're at above the water level here. So in order to equal that out, this water moves to the other side. Even though that other side has more water, it still moves to that side to try and balance it out and try to get back to equilibrium. Okay. So this is analogous to what happens when you put a hot object in contact with a cold object. And that's what this whole analogy was supposed to be about. So if we take a hot object and we put it, which is the temperature's above that line, and we put it in contact with a cold object, then what's going to happen is the thermal energy will flow from the hot object to the cold object until the temperatures are the same. Even if the cold object starts out with more energy because it's bigger. Okay, remember, if it's bigger, it has more, it would be considered having more energy just because it has more particles. Okay, but still, we take that hot object, put it in contact with a cold object, the energy is going to flow from the hot to the cold, regardless, to try and get that temperature to be the same, the temperature of both objects to be the same. So if you don't like that analogy, fine, you don't have to have it. You just need to remember this part. The thermal energy always flows from the hot object to the cold object until the temperatures are the same. Okay? The temperature does not depend on the total amount of energy in an object. That's why we said temperature is a measure of the average kinetic energy. So it only depends on the average kinetic energy of the particles. Okay, so that's really important thing for you to write down and remember for the rest of this particular unit. Okay. So imagine putting a hot brick in contact with a cold brick, as shown in the figure below. So you got your hot object, you got your cold object. Rapidly vibrating molecules in the hot brick collide with the slower vibrating molecules in the cold brick, causing the molecules to vibrate more vigorously. So these molecules here are moving really, really fast, and they collide with these molecules here that aren't moving quite so fast. So what happens is these molecules speed these guys up. Okay, so they give some of their kinetic energy to them, and these molecules wind up moving faster than they were as a result of being in contact with the hotter molecules that are vibrating more rapidly. So here's just another way of saying that. The higher speed molecules in the hot brick collide with the slower moving molecules in the cold brick, transferring energy to them. This energy transfer increases the temperature of the cold brick and lowers the temperature of the hot brick so that eventually they will be at the same temperature. The energy transfer continues until they both reach the same temperature, and we call that thermal equilibrium. A system is in thermal equilibrium when its temperature is constant. Okay, so that's an important thing to remember. And there's no net transfer of energy. So if something is in thermal equilibrium, like I said, we need to understand the correct vocabulary and use the correct vocabulary. So something is in thermal equilibrium when its temperature is constant. It's not changing anymore. There's no net transfer of energy. that point, we say that something is in thermal equilibrium. Okay, so this is important to remember as well. Objects in contact with one another are in thermal equilibrium if they have the same temperature. It does not matter what the materials are, what mass they are, what shape they are. That is makes no difference. You got two objects, one hot, one cold. You put them in contact with each other. The hot object will transfer energy to the cold object until they have the same temperature. And at that point, they're in thermal equilibrium. It does not matter what their shape is, what their material is, doesn't matter at all. So this is sometimes called the zero law of thermodynamics. Remember, there are three laws, first, second, and third, and would be the zero one. That energy is always transferred from hot object to a cold object, and thermal equilibrium is when they have the same temperature, or there's no net change in the energy of those two objects. Okay. We'll get into the other laws of thermodynamics in other sections of this chapter. So when a cool pan of water is placed on a hot stove, the fast particles in the burner collide with the slow particles in the pan, causing those particles to speed up. This energy transfer is called heat. Okay, so when you set your pot of water on the stove in order to heat it up, what happens is the particles in the stove are moving faster and faster, and so they transfer their energy to the particles in the pan, which start to speed up, which transfer their energy to the particles in the water, which start to speed up. That is energy transfer is referred to as heat. Heat is the energy that is transferred between objects because of a temperature difference. That's the definition of heat. It's the energy transfer between objects because of a temperature difference. Okay? An object does not contain heat. It contains thermal energy. So please make sure you use the correct vocabulary in your explanations and justifications of things. An object does not contain heat. Okay? It transfers energy in the form of heat. It does not contain heat. It contains thermal energy. Heat is energy, so it is measured in joules. So you might need to go back and refresh your memory about what a joule is. Okay, so a variety of temperature scales are used in everyday situations. Celsius, Fahrenheit, and Kelvin scales are the three common ones. Celsius is your metric scale that we typically use more, that we usually are the ones that we use. So Celsius scale is named for Andreas Celsius, and in his scale, of course, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. The choice of the zero level is kind of arbitrary. So, as is the number of divisions between those two reference points, between the zero and between the freezing and boiling point. In the Fahrenheit scale, it's not 100 divisions because we go from 32 to 212. In the Celsius one, it's from 0 to 100. Okay. There's no upper limit to the value of temperature in a Celsius scale. However, there is a lower limit. The Celsius scale, the lowest possible temperature is negative 273.15. Stop. All right, Fahrenheit, which we don't really use very much because we do everything in metric system, but 32 degrees is your freezing point, 212 is your boiling. The Fahrenheit scale not only has a different zero than the Celsius scale, but also different sizes of degrees. So between 32 and 212, there's a 180 degree span, whereas from Celsius, it's only a 100 degree span. So So there are the conversions between temperature and between Celsius and Fahrenheit. Now, experiments show that there is a lowest possible temperature. The lowest possible temperature is what we call absolute zero. And this is the temperature below which it is impossible to cool an object down. I mean, you can't get any lower than that. Absolute zero can be approached, but can never be attained. Careful measurements for that absolute zero show that it is negative 273.15 degrees. Now, let's look at the Kelvin scale. The Kelvin scale is based on the existence of absolute zero. So it makes the 0 point the lowest possible temperature, meaning you can't go below that. So the 0 point on the Kelvin scale is abbreviated 0K, and it is absolute zero. So there are no negative temperatures in the Kelvin scale. The degrees on the Kelvin scale have the same size as the degrees on the Celsius scale. So between the freezing point and the boiling point is 100-degree division. It's the same number of divisions. So the conversion between Celsius and Kelvin is given by adding 273. If you remember in chemistry last year when we did all of our gas law problems, they always had to be in Kelvin. And we got that by taking our Celsius and adding 273 to it. All right, and that's just a diagram that shows the different scales. All right. And that is it for 10.1.